Okay, we're going to get started in earnest now. Welcome to the University of Idaho and Montana State University Integrated Design Lab Spring Series. We have 6 sessions, I believe. Tonight is the first. I want to take just a couple minutes and do a couple orders of business. One is, as always, thank you to Idaho Power, Northwestern Energy, and Better Bricks for sponsoring our speaker to come out. Folks in the room, there are restrooms upstairs and downstairs. Folks online, feel free to email kevinv@uidaho.edu and interrupt us with questions. I will do my best to relay them to our speaker. And those in the room also, please sign in. It's very important that we capture names for continuing ed and to keep speakers coming. I'm going to go really quickly through the dates of the sessions and the titles. Please take a look and grab this off the back table. That will give you the information for the rest of the series. Tonight, I'll introduce last. So our next presentation is April 9th. We have Micah Allen talking about the reality of energy performance compared to energy modeling from eSource. Thursday, April 16th, we've got Guy Newsham coming from the National Research Council of Canada in Ottawa and talking about photo control dimming and everything you wanted to do with photo control, but we're too scared to try. On April 23rd, we've got Chris Meek coming from the University of Washington talking about architectural forms and daylighting. And May 7th, we have Doug Avery coming from Southern California Edison talking about the Office of the Future project. And the last presentation will be May 14th. Jo McQuinn from our local Idaho Power talking about her program, the new program on demand response from Idaho Power Company. So that's the last time I'll give the detailed intro. From there, I'd just like to say thanks for coming, and thanks to Michael Utzinger for joining us from the University of Wisconsin-Milwaukee. Michael, Mike as we call him, was an old professor of mine, not old, he's just a previous professor of mine when I was at the University of Wisconsin-Milwaukee. I grew up in Green Bay. Spent 4 years with him. We actually didn't cross paths much because he was a chair at the time. I was a student. I was just a lowly student. And he was doing great work then and is still doing wonderful work. He's both an architect and a mechanical engineer, so he's schizophrenic or internally conflicted, as they might say, metaphorically speaking only. He's a registered architect, a licensed PE, and degrees from Urbana-Champaign, and his Master's of Science in Mechanical... Master of Science in Engineering from Wisconsin-Madison. So with that, thank you for coming. He's going to talk tonight about an interesting project, but it also encompasses a larger array of integrated design approaches, specific strategies, as well as a nice overview of what the U.S. Green Building Council has excuse me, this will just keep ringing otherwise. What the United States Green Building Council has, I believe, adopted as their innovation credit for the carbon neutral operations for buildings. So he essentially wrote the credit. So with that, thank you for coming, Michael.
Thank you very much, Kevin. I'm delighted to be here. This is actually, I've traveled across Idaho twice. This is the first time I've actually had a chance to spend some time in Idaho, and I'm delighted to be here. What I'm going to talk about is a building, the Aldo Leopold Legacy Center, and I want to both talk about the design process that went into it and then the actual performance and the measurement of the performance. This is actually the third project that I worked on with an architectural firm in Wisconsin, Kubala-Washotko Architects. The third in a series of high-performance green projects we've worked on. And while I'm primarily going to speak about this one, I hope to also bring in some of the lessons learned along the way from those projects as we look at them. While I teach, I do try to be involved in the profession. It does mean that students see less of me, but hopefully they get more out of it the times that they do see me with what I bring in from experience in the profession. Now, The Aldo Leopold Foundation is a foundation that has been organized to promote ideas of a land ethic. Aldo Leopold wrote a book in the late 1940s called the Sand County Almanac that ends with a statement of a land ethic, of our attitude and our relationship to the ecology around us. Some of you may have heard some of the arguments going on right now about extending rights or ethics to the other great apes or other primates. There's been some discussions of that. Leopold at the time was talking about extending the idea of an ethic and an ethical relationship to the biota that was around us. And the quote that you're looking at on the screen is from a lecture that he gave at the University of Wisconsin in Madison in 1938 to the College of Engineering. At the time, he was professor of wildlife ecology after having set up the Department of Wildlife Ecology at the University of Wisconsin-Madison. And the photograph is of the pines that Aldo Leopold planted around the shack where he wrote a Sand County Almanac. And those pine trees, red and white pines, which were planted in the late 30s, had grown to a point where by the late 90s, they had no longer grown anymore. They basically needed to be thinned out or weeded out. So they knew they needed to thin out a forest, and the Leopold Foundation also was expanding and needed to move out from the Victorian home that they were renting in Baraboo as a headquarters. So the foundation decided that they wanted to have a new building and that the material for the new building should be pine tree that were harvested from the forests that had been planted by Aldo Leopold and his family. And the approach to harvesting was to harvest the understory, keep the best trees in the forest, and allow the forest to be maintained and grown to a mature forest with the largest standing mass of carbon possible in the forest. So that was a bit of the idea that the foundation had. So it was within their mission to, when they looked at doing a new building, to ask that the design team design a carbon neutral building. This was in 2004. There were no written design methods for doing carbon neutral buildings, and there weren't really any that we had read about that had been measured that way. The architectural firm took on this task and brought me on as an environmental consultant, and we spent a good portion of the period of programming trying to define exactly what that notion of a carbon neutral building would be. And at the end of that programming session, which did include a certain amount of research into performance, we had a post-programming goals meeting. And as I've gone through the process of designing high-performance buildings, I have come to the conclusion that this is actually a very critical point in the design process, even more so than prior to the program. After some programming and research goes on, getting together the client, in this case the foundation board, the design team, and all of the consulting engineers, along with the construction manager and the team that was going to be doing the building simulation, were all brought in at this point after the programming and some schematic design. And the owner's commissioning agent, who was contracted separately, was also at this meeting. And we had an excellent commissioning agent on this project, Ron Perkins from Super Cemetery. And the group spent an entire day defining the goals of the project. And once those defined goals are set, it actually becomes very clear what the task of the design team is in performance. And so one of the issues was we had to define what we meant by a carbon neutral building. And we decided that while energy flows and resource flows were reasonable in terms of understanding in the design process and measuring afterwards, we might be able to define a carbon neutral building relative to the building operation. We felt it was too difficult at that point in time in 2004 to track down the carbon footprint of everything that would go into the building, all of the energy consumption of all of the people that were building it, driving back and forth to the site, the embedded carbon emissions in everything from photovoltaic panels to mechanical systems. So we drew a boundary around the operation of the building, and we decided that we would try to document everything that went into the building very well so that it would be a database that could be mined later to look at what the carbon cost of construction was, but we wouldn't actually include that in our definition of a carbon neutral building. We also decided that if it was going to be a carbon neutral building, it should be a net zero building. Net zero, we defined at that time, and it is similar to one of the DOE definitions now, would be that the energy generated by renewable energy on site over the course of the year would be equal to the energy demanded by the building over that same period of time. So that what we would develop on site from renewable energies would be equal to the building's demand for energy over that period of time. We made a decision at that time that the building would be all electric. Well, actually, we added to that some wood-burning stoves. This building is located in a rural area of Wisconsin that has a reasonable amount of woodland, and half of the staff of the Aldo Leopold Foundation do heat with wood. I come from Milwaukee and am not as large a fan of biofuels and wood heating, but we decided that still was a renewable energy. So wood heating and all electric would be the energy source. And we also decided that we would take grid electricity and use solar photovoltaics, which would generate more electricity than we needed in the summer, but we would need more electricity from the grid in the winter. So that was sort of the basic structure of the definition of being a carbon neutral building and of what we were defining as net zero. Now, I believe that one of the most critical issues in establishing goals in building performance depends upon how well you know and understand how buildings perform, both yours and others. And part of our research included understanding a little bit about what other high-performance buildings were doing. This graph illustrates what is the energy utilization intensity in thousands of BTUs per square foot per year of a median office building from everything from the 1960s all the way on up and earlier. So a great deal of energy use there, around nearly 100,000 BTUs per square foot per year. Two buildings from a study of 6 high-performance buildings by the National Renewable Energy Laboratory, the Chesapeake Bay Foundation, which was the nation's first LEED Platinum building, and the Lewis Center at Oberlin College, designed by William McDonough, a high-performance building coming out of his office. Those two buildings were reported by the Department of Energy. The building in between in there, the Schlitz Audubon Nature Center, is the first high-performance building that I worked on with Caballo Oshatko Architects. So that was one of the buildings that we had worked on, and one of the things that we do on projects is we get the client's utility bills after the first year of operation, and we look at what their actual energy consumption is relative to what we were predicting. It's a way of getting feedback on your design. Yes?
I got a question about the chart, and that's how the energy is used. So where you have green and pink, the pink means PV energy that's used by the facility, not synthetic.
Correct. Well, this is based on net, so it would be in the case of Lewis Center at Oberlin College and Woods Hole, that's reported as net uses. So you're measuring everything coming in from the utility, and then the PV is what you're using on site from the PV, so that the length of the bar is the total energy demand. And so there, and the PV is the total of what's generated by solar, so that actually some of that PV could be going into the grid and some coming back from the grid is coming in, but you're seeing it only as the PV generated. So that it's kind of the net flow from the grid, so that the total length of the bar represents the building's annual energy demand.
So in the Oberlin case, it's about half.
At that time, although they've actually increased the PV array since then, and I think they're very close to being net zero now. And then the last project there, the Woods Hole Research Institute, is another William McDonough project, which I had actually visited when this project had started on I look at buildings on my summer vacations and things like that. It's a thing to do as an architect. My children wonder about their life and stolen vacations along the way, but the Woods Hole Research Institute is in Cape Cod in Massachusetts, another William McDonough project, and was the lowest energy utilization intensity of any of the buildings that we had seen up to that time. And that became our goal. That's around 15,000 BTUs per square foot per year. Actually, our goal for this project was 17,000 BTUs per square foot per year. We set that up as a goal, and then it was the design team's requirement, basically, to come up with a building that would fit within that goal or that budget. And once you set that up as a goal, it's very easy to say, okay, how many square feet of photovoltaic panels am I going to need to produce that amount of energy during the year? And that ended up being a photovoltaic array that would generate about 50,000 kilowatt hours per year, or something on the order of a 40 kW peak photovoltaic array. And what, you know, I've read a few different opinions out there that say the first thing you do is get the building's energy demand down, and then you can worry about adding solar to it. Well, I would say when you're doing net zero, if you're setting as a goal 17,000 kBTUs per square foot year as a goal, you have set a very energy efficient building up as a goal. And what you're now doing is looking at what it would take to meet that energy efficient goal with solar energy. And the advantage to the client was that the client had in the budget the money for the photovoltaic array at the beginning at a scale that the client was assuming would basically provide them with solar energy annually equal to what the building would demand. This particular building was built in a utility district that did not allow it to get any support from the state of Wisconsin or from the local utilities. In addition, because the Aldo Leopold Foundation is nonprofit, there were no federal advantages. Tax credits do you no good when you pay no taxes. So the Aldo Leopold Foundation paid for this PV system without support. The PV system will never be economically viable. All of you who have an automobile that will return on your investment over its life, can you raise your hands? We choose to judge many of our devices in different ways. They chose to judge these systems as systems that would provide power without generating CO2 emissions. That's as important as getting a Mercedes that can handle well in potential accident situations, or Audis. I mean, we choose our devices for a variety of things. Energy efficiency is not the only way to judge our devices if we're talking about environmental issues. We set up at that meeting a series of building and design strategies, the kind of things that we thought about since we had everyone there as a group in a sort of a brainstorming notion to work at. And I'm dividing these strategies, even though they were discussed at that particular meeting, into building design or shell strategies and HVAC strategies. I'll kind of go through them quickly. And the building design strategies, one of the ones that is, I think, less talked about and really very interesting is the notion of all of the issues that you do when you're programming the spaces. If you want to do a building that's going to be, let's say, naturally ventilated, and you would like to be able to, when you're naturally ventilating the building, turn down the HVAC equipment or turn it off in the same way you would turn your air conditioning off in your house when you open windows, then all of the occupied spaces need to be perimeter spaces so they have access to that natural ventilation. And it is actually very difficult to program buildings to be totally naturally ventilated and to get to a situation where you can actually turn off the mechanical system. This was our third try, and we finally got a building that we were able to do it that way. The other issue when you're programming is think about the thermal requirements of the zone. The Aldo Leopold Foundation does a lot it does a good deal of teaching for forestry management practices, for prairie restoration. A lot of their teaching is on land conservation and land management practices. And most of those classes take place starting around mid-March and operating through October. So the seed hall is where a lot of those classes take place. They can have up to about 120 people in there. There is no HVAC system in that building. It is only operated from mid-March through late October. There is a wood-burning stove. There are window panels that can be removed and replaced by screens. It's basically a screen porch that's not attached to a building. And the windows aren't removed until you get to the main summer condition. There are some transoms that can be opened in spring or fall for ventilation. So it's basically a naturally ventilated building with a wood heating stove and no other mechanical system. Again, I mean, that's occupiable space, but it's not mechanically conditioned space. The workshop and garage, it's like a farm building. There is no mechanical heating or cooling in the workshop and garage. When the staff or the interns are working with that equipment, they're typically working outside. They're dressed for being outside, and so working in and out of the workshop is, again, not much of an issue. So that's also an unconditioned building. The administration and exhibit space has a radiant slab for heating and cooling and is the main sort of occupied space. The conference wing, they said, well, this is for more formal, smaller meetings in a nice conference room. We won't use it more than once a week. So in the winter, let the mechanical system just heat it to 55 degrees. We'll bring it up to temperature with a wood heating stove whenever we occupy it. And they wanted that conference wing on a wood floor rather than a slab on grade. So that has a slightly different system. There's actually fin tube convectors rather than radiant slabs in that system. But again, thinking about the program, thinking about the uses, and looking at how you adjust systems relative to those uses. This is the interior of the seed hall without the HVAC system. And I have down at the bottom gross areas, occupied areas, and conditioned areas. One of the issues when you're looking at performance criteria is knowing what the measurement value is. And depending, it can be more important to use one or the other. The conditioned area is only the main office, exhibit space, and the conference wing. The occupied area is a good 14% larger than that, and the gross area is a bit larger. I believe in general we should use gross area as a measurement. I think when you do designs where you have spaces that are not mechanically conditioned, you don't want to penalize them by taking that out of the calculation. I feel a sneeze coming on, pardon me. Okay, but in any case, the NRAIL study, for example, doesn't say whether the areas they're working with are gross or net. And I think at least it's critical to have an understanding of what terms are being used when you're providing that. I'm not going to go in as much detail in some of these because I think most of you know that super insulation is critical. We basically had R20 to R60 for opaque walls. We used high efficiency glazing with argon fill, but it's still a small building, so infiltration rate is fairly extensive. The net heat transfer rate, and this is actually per gross square foot of the conditioned building here, rather than taking in the unconditioned spaces, since this is what the HVAC system has to work against. It is basically 1/5 of a BTU per hour per square foot of floor per degree Fahrenheit. We did do some passive solar strategies, but in a slightly different fashion. There's a public corridor that runs along the south side of the building that connects the entry foyer to the sort of formal conference room and meeting spaces. It allows the offices to be closed off as visitors basically pass by. But we made it so that doorways between the office spaces and the windows between the office spaces could be opened. The concrete inside the office spaces is stained dark. It's left unstained in this hallway, so there's more of a light bounce up from that hallway to add light into the spaces. That public space also reduces some of the glare in the main office spaces by basically catching a lot of that low south-facing sunlight in a circulation space rather than a workspace. The total glazing area in the conditioned building is around 20% of the floor area. And so it's not as much glazing as a lot of architects typically are pushing for in buildings. We use north-facing skylights, which you can see in both of these windows. The lower the lower window on the left is the double 3-foot 4-inch square windows that are in the 9-foot square individual offices. They also have glass and sliding glass doors opening into the main office workspaces. So basically, most of the glazing is facing south or north. Around 13% of that 20% of the floor area. The rest is half east and half west. The average light levels measured in the spaces are typically 20 to 40, 60 foot candles. And again, as I said, the building was to be made with wood that was grown on site. So, and I'll come back to this towards the end. All of the heavy timber construction in here are pine that were harvested on site, that were milled on site. The walls, surfaces on the interior are pine. The ceiling surfaces are red maple, all harvested on site. Just about 92,000 board feet in 13,000 square foot of building that was all harvested on site. Generally, the occupants don't have automatic light controls. They simply don't turn the lights on. And I actually think it's interesting to go into a building that doesn't have the lights on. It's very difficult when you walk into a building that has electric dimming controls to tell whether or not they're operational or what's going on with them. And the general impression is we turn lights on in all of our buildings but our houses. And we try to change that notion a little bit and say if it's daylight outside, turn the lights off. We did work quite a bit on shading strategies. I think it's critical to reduce the cooling demand in the summer by proper control and shading. Most mechanical engineers treat the perimeter of a building as a higher cooling load than the interior of the building because of solar gains. And it's actually hard to find mechanical engineers that you can work with on shading strategies and reduction of those gains because they figure, oh, they'll go out and value engineering and I got to be sure I have enough equipment for assumption that there's no solar control on the glass. But we work very hard to try to get a good reduction of the solar gain in the summer. It does take it out somewhat in the winter, but I think that's a critical part of good design. On natural ventilation, we actually modeled natural ventilation in the simulation. We integrated a multi-node bulk flow model, CONTAM, which is from the National Institutes of Standards, with our simulation program Transys, and we modified it so that we could vary the amount of window openings depending upon what the temperature is outside. In other buildings we've done with natural ventilation, we find that as you move into the cooler periods when the outdoor conditions like today, people might like ventilation, but they'll tend to crack the windows. Whereas if it's 65, 70 degrees outside, people will open the windows up wide. And so we worked out a control strategy that would vary the amount of window opening depending on whether the outdoor temperature was above 50 or up to 100% open at 75 degrees. HVAC strategies. This building uses a water-to-water ground source heat pump that generates hot water in the winter and chilled water in the summer. It's a seasonal changeover system. In the shoulder seasons in spring and fall, we've got operable windows and we've got some wood-burning stoves. So there's different ways to provide cooling and heating in that kind of a changeover system. The radiant floor slabs are used for heating and cooling. It's now becoming my experience as I do more of these buildings that it is appropriate to provide the sensible heating and cooling loads, to use basically the mass of the building and radiant sources for the sensible side, use air for the ventilation requirements and the latent portion of the load. You pay about almost 20 times as much energy to move a BTU of energy with a fan than you do with a pump and water. And so using an air system for all of your air conditioning needs generally means a fan that's about 4 times as much as what you need for what we actually breathe. And there's a huge energy penalty on that. So we've been working to try to move as much of the thermal load over to water systems and radiant surfaces and away from air systems. We use displacement ventilation. We basically have 100% outdoor air ventilation, and yet our CFM requirement per square foot is about 20% of what a typical building with a VAV system would be. So it's a large reduction in that area. We used earth tubes for air pretreatment. That is, air goes into basically sewer pipe underground and then comes into the air handling unit. And we also do use enthalpy recovery ventilators. We did as much as we could to minimize the flow friction and maximize the efficiency of pumps and fans. And that was a real learning experience for the mechanical engineer, and one of the things the commissioning agent, who was very good at a lot of the fluid flow issues, hit them on. The mechanical engineers redesigned from the original design all of the pump systems for the earth loop and for the floor slabs, and the installed horsepower went down by 80%. They used ASHRAE standard methods in the original design. And but by working a lot harder, enlarging some of the ducts for flow, reducing flow friction requirements, changing the relationship on series and parallel flows for the wet ground wells, we really were able to maximize the efficiency of the piping systems, and wherever possible, we used variable frequency drives on larger pumps and on the main air handling unit, and variable speed pumps and fans on all of the smaller ones. The water-to-water ground source heat pump meant that we were using in a central system. We had 3 6-ton heat pumps all tied in parallel together to basically provide hot water for the heating coil and the floor slabs, and chilled water for the heating coil, now a cooling coil in the summer, and the slabs. Now, we might have a very small load in one of the radiant zones in the floor slab, and we wouldn't want to turn on 1, 2, or 3 6-ton heat pumps for what might be a half-ton load at a particular point in time. Heat pumps you really want to balance very well to the load that they're carrying. And so what we did was we added a 500-gallon tank as a kind of a thermal capacitor. And that tank is a hot water tank in the winter. This is all before the insulation went on all the systems. And it's a chilled water tank in the summer. We run it in the winter from 105 to 115. The temperature that we're running it at is primarily what we need at the heating coil in the air handling unit. We have a mixing valve on the return loop on the floor slab to basically drop it down to the 75 to 80 degree temperature we try to run the floor slabs at. What happens is when that tank drops down to 105, the heat pumps go on, and basically they're working to heat up at 500 gallons of water. So they can operate at a very efficient duty cycle, refill the energy in the tank, and then you dribble the energy out to the building as you need it. It goes out of the tank and then you bring it back up again. You've got geothermal energy here. We don't have that in Wisconsin. We would have made maybe different decisions if we were here in Idaho and had access to something different. And we probably would have looked at evaporative cooling much more carefully, which we don't really have available to us in Wisconsin. So, you know, I give you all of our decisions, but they're based on our context in a way. And so but basically working with heat pumps and working with a ground loop, we basically set up a hot water tank and a chilled water tank that the heat pumps charge, and then we dribble energy out to the coils and the slab as we need it. And this is a little bit of a faint diagram, but there's 16 wells for the main building and 6 wells that all the wells go down about 225 feet for the for the conference wing, those are in this area here. The mechanical mezzanine in the conference wing, and the lines for the fin tube convectors for heating. The cooling coil with the ventilation system is in that unit. Here's the 500-gallon tank. And you can see that the radiant slab has a number of different zones. The area where there is not any radiant slab heating is right here. That's the janitor's closet and the server room. Server room doesn't need heat. It has its own heat generation very well, and you're basically ventilating it potentially 24 hours a day in the summer when it's warm. And then these are the sewer pipe over here for the air intake, manifolded out to 4 100-foot long ducts that the air comes in over to this space over here. And we actually have separate temperature controls in different areas of the slab, so we've been able to moderate slab temperatures according to the proclivities of some of the occupants. There is one staff person who likes her slab much warmer in the winter and much cooler in the summer than everyone else. And we actually can modify that. It's a very small energy bit to pay for some occupant satisfaction. Now, we use simulation to model components. I mean, our approach to the simulation was to begin modeling the shell as it's being designed and look at the loads on the building shell, look at the solar controls on the shell, some of the ventilation issues. And at the same time, we were building up the mechanical system kind of piece by piece in a separate simulation model that we would then link together. And none of us had ever worked with earth tubes before, so we said, all right, we better take a look at this. We got a model for it from Switzerland, and the blue dots are the outdoor inlet conditions throughout the year in terms of dry bulb temperature and humidity ratio. And so you can see the 100% line on the psychrometric chart running down the edge of this curve. And you can also see that the yellow dots, which are the outlet from the earth tube, are running all along that saturation line. That is, we're getting condensation in the earth tube. And you can see up at the top of the chart that condensation is actually doing some dehumidifying as well as cooling the air. So there's a lot of cooling that's going on, but not a lot of heating. This is looking at an enthalpy recovery ventilator. And here you don't see the conditions running up to the saturation line on the psychrometric chart. An enthalpy recovery ventilator is basically taking what is leaving the building and using that to modify what's coming into the building. The earth tube is basically taking the air coming into the building, modifying it in that subterranean environment in the duct, and bringing it into the building. And so an enthalpy ventilator does a much better job in the winter at recovering heat that would otherwise be leaving the building. In our climate in Wisconsin, it really doesn't do much at all in the summer, and you're better to actually bypass an enthalpy ventilator in the summer, because our outdoor conditions are so close to the indoor conditions that there's nothing to recover. Whereas the outdoor condition, where there is some humidity, when it's going down into the earth ducts that are running closer to the ground temperature of around 55 degrees Fahrenheit, there's a lot more pre-cooling that's going on there. The enthalpy recovery ventilator, if you looked simply at the energy content of the air coming into the building, was a little bit better than the earth tubes. What they did in the winter overcame what they didn't do in the summer. But you have a large friction loss in the fans to push through that heat exchanger for an enthalpy recovery ventilator. So you're adding a pressure drop to the fan system. We didn't have that in the 2-foot diameter sewer pipe that we used for the earth tubes. And so when you added the parasitic power in, the earth tubes work better. So we put the parasitic power in, but all of you know anytime you're doing something new in design, you always miss something. We have a UV lamp for, along with a metal filter that is painted with a titanium dioxide coating to basically respond to anything in terms of bacteria or fungus that may generate in this moist environment. And that UV filter was what we decided on doing. Well, once we actually specified and it came in, lo and behold, it's 300 watts, and they said, no, you want to run this all the time. You don't want to turn it on and off. Well, that 300 watts probably overcame whatever we were saving in the fan horsepower. So you do learn along the way, and when you're doing new design, there are lessons that you learn both as you make good design decisions and beyond. 100% outdoor air and displacement ventilation. Basically, this diagram is probably a little bit more detailed to get a whole bunch of information out of it. It's mainly, we basically have the radiant floor slab and the air coming in low from the air handling unit, which is a VFD drive fan. Then all of these spaces, diagrammatically all of the occupied spaces, have direct exhaust to the outside. Okay, so we're basically carrying the air through and exhausting it. We do have the exhibit space set up, so if there's a large group and we have to add more air, that additional air comes with an enthalpy wheel that adds another 750 CFM, and we're doing some energy recovery. Thank you. The other issue here, we've got a 40 kW PV system, and so we've got a lot of waste heat coming off the inverters. And we have a single coil in our air handling unit. We need to do some reheat on the air system in the summer. So we thought we would put in a fan to go through the inverter room and a heat pipe to do basically a little bit of reheat on the air going into the building from the heat pipe. And we put that in, and the heat pipe didn't work as well as we thought it would. Well, part of the problem was in the 3 years between the two projects, the project before this one and this project, inverter technology had gotten better, their efficiencies were better, and their waste heat had dropped. So we didn't have as much waste heat as we thought we would. And it seemed to dissipate pretty well into the basement walls anyway, so there wasn't a lot of availability. But the other thing was this heat pipe seemed to be working in reverse. It was taking energy in the wrong direction, and so we pulled the heat pipe out and put a reheat coil in that came off of the service hot water system. The client actually said, we know you're doing what hasn't been done before, you're allowed to fail. So the client didn't even hiccup hard when we pulled an $8,000 heat pipe out and replaced it with another unit, because they felt that was part of what they were doing in the learning process of this project. You don't get clients like that very often, but you rarely get clients that ask you to do a net zero carbon neutral building. And so when you get one that behaves like that, that's really a very nice thing. Now, the only bits, I already said quite a bit about efficient flow systems, but just a couple of numbers that you can use to sort of check your own designs. The pumping power on this building, and this is per gross square foot of the conditioned area. Okay, so if you're doing a fully conditioned building, gross square foot of that area. The pumping power is 0.3 watts per square foot, and the efficiency is about almost 41 BTUs of heat transferred per hour per degree of temperature rise in the fluid per watt of pump power. For fan power in this building, we're at 0.29 watts per square foot, and we're able to transfer 2.3 BTUs per hour per degree Fahrenheit of temperature rise in the air per watt. And I should point out that all of the fan systems and pump systems in terms of GPM per watt or in terms of CFM per watt are way below the values that ASHRAE holds as what you should be meeting. So there was really, there's I think a large area of efficiency improvement in fan and pump systems that is an area that we can really mine in our buildings. We modeled controls by simulation. Energy Plus is a program that works like Transys, that is what's called a temperature level model. You integrate your equipment, your controls model, and your building shell all together. The dots are the conditions in the front office and the main office in the building without dew point control strategies. And so this is the the orange here is the ASHRAE standard 55 winter comfort box for one clo, and the greenish here is the summer comfort box for 0.5 clo, and you can see there's quite a bit up here that is outside of what you want in that range. And we moved to a dew point control, both for better control interior in the office space and also for better warnings in natural ventilation if we were going to run into problems of condensation on a chilled slab. And this was sort of the first round with the dew point controller, and we could just throttle the temperature we wanted for the dew point down and bring all of that within that range. Our time steps on this building on the simulation were 5-minute time steps. We've gone down to 1-minute time steps. And in terms of controls, we'll use the temperature from the previous time step to make a control decision in the current time step to initiate a piece of equipment dumping energy into space or removing it from space. And so we will get very detailed in simulations where we feel it's necessary, and we'll go back and do measurements afterwards. This is the first year graph of the measured and modeled performance. The red line is what's called the energy cost basis. That would be the ASHRAE 90.1 model of the building. The black line is not the design energy case, but what was our net zero or carbon neutral design case. We modeled occupants working with natural ventilation. We also modeled occupants turning light switches on and off. LEED does not allow you to model occupants touching light switches. If you do not use automatic controls, LEED tells you have to assume the lights will be on all the time. So our design energy case model had the lights on all the time. Our carbon neutral design model had a occupant switching controls that was based on the exterior solar radiation that was available. And that's the model that is shown here, and the actual net metering is shown, and this is basically zero means that above zero actually is good. That's what you're selling to the utility. Below zero is what you're purchasing from the utility, which is always happening in the energy cost basis model, which assumes no site-based energy generation. And you can see that we didn't do as well in the winter, but we're doing pretty well in the summer. I want to go into a little bit of detail on some of these and then talk about the carbon neutral aspects of the design. This is the light usage. We sub-metered lighting, and they generally don't turn the lights on. So compared to leaving the lights on all the time at almost 22,000 kilowatt hours, they're effectively only operating lights 1/3 of the time. This includes night. This is winter conditions. In other words, throughout the year, that's the amount of light usage in the building. And so even though the USGBC in green says you cannot model occupant usage of lights, if you treat people as intelligent human beings in their building and give them reasonable controls, you might actually get them to do the right thing. On the other hand, we do a lousy job of modeling plug loads, and I mean that both individually on this project and collectively. Our modeled plug loads were the same for the design energy case, the energy cost basis, and our carbon neutral model around 10,000 kilowatt hours per year. Actual plug load usage is around 17,000 kilowatt hours per year. So that just ate away everything in the difference on the lighting savings, and is why our summer models look pretty much right on. In the workshop and the seed hall, we also underpredicted by a factor of 3 what the actual usage was. And you know, the plug loads are really based on what the client is often buying and using, but we found out a couple of other things. We had told the foundation to turn computers off at night. We've done some measurements. If you leave your Dell computer here on and don't turn it off, over 13 hours at night, it'll consume a little over a kilowatt hour of energy. So with weekends and everything, that's about 365 kilowatt hours per year per computer. It adds up very quickly. The IT people that they hired for their system said, leave your computers on at night because we're going to do all of our upgrading at night when you're not there and you're not going to bother you. Unless you're doing simulations, unless you're doing high performance CAD modeling, most people at computers do web surfing for the business or not, email for the business or not, and work on Microsoft Office. And their usage is not that great that it's not impossible to upgrade the systems during the day. And it just is set to basically on restart install everything that's been upgraded. So there's a problem between what IT people typically recommend to occupants and what really works for energy conservation. There's a variety of different things that have come into this, some of which we're working to reduce on this side with the client. The conference space had this elegant wood-burning stove in it, which was a lousy performer. And it couldn't bring the temperature up from the 55 to 75 degrees. So in the first year, the heat pump was running 100% of the time because they were trying to use it to heat up the space. We designed the heat pump for this space to, on the design condition, it was sized on the design condition to bring the temperature to 55 degrees. That was it. We did not put a factor of safety in on the equipment. We're mucking around with how you size equipment from simulation models and whether or not it is a good thing to oversize HVAC equipment in buildings or not. And so basically, it appeared as though the heat pump wasn't working, but they replaced this wood-burning stove with a much better cast iron piece that does radiate energy out fairly rapidly when you put a nice load of wood into it. That now brings the space up to temperature for them for meetings, and the space maintaining 55 degrees with the heat pump system has worked very well. So that's one of the things we've learned after the first year. Now, I want to go back to that graph and add the Aldo Leopold Foundation into the graph on measured performance. And I also have added two other sort of standards in here. The Department of Energy and NRail have done a series of base case buildings that are designed to ASHRAE standards. Hospitals, restaurants, warehouses, offices at 5,000, 50,000, and 500,000 square feet. They all, and they've done them in all of the different climate zones in the United States. So they're available. You can get all of the output on them. They're really quite detailed. What I'm showing here is the average of the Chicago and the Minneapolis models. Baraboo is about Wisconsin is about halfway between Chicago and Minneapolis. And that's suggesting that the code-based energy utilization value, according to the Department of Energy, for an ASHRAE building designed in fall of 2008, would be somewhere between 65 and 68,000 BTUs per square foot per year. Those are all the other buildings I had in there, and then at the bottom is the Aldo Leopold Center. We did not model the wood-burning stoves. We figured that it was going to be a little bit difficult to toss that in. We didn't know when they'd run the wood-burning stove or they wouldn't. So we just didn't model them and assumed that the wood-burning stoves would do whatever they were looking for it to do. But in an analysis and in a carbon counting, I didn't want to ignore it. So we did use measured amounts of wood. They set aside 2 cords. They ended up adding 3/4 of a cord more. This year, they're probably going to use under 2 cords. When I show them what the percentage of wood burning was to the overall energy use, a little bit more than 5,000 kilowatt hours per square foot per year, they have gotten a different understanding in the larger scale of what wood burning means. And so that is included in this model. But we didn't include it in our model that we were working with. So if we were talking about as a goal being somewhere around 15,000 BTUs per square foot per year, we actually ended up somewhere around 19,000, and we've got about 5,000 BTUs per square foot per year net coming in from the grid. So we didn't meet net zero, but we really did come very close, and we're going to come even closer at the end of the second year. And this going back and revisiting your buildings, I think, is something that we as professionals haven't been doing, but I think it's the only way to really get a handle on what it is we're doing as design. And the last item that I wanted to touch on was this was also designed to be carbon neutral in its operation. And the World Resources Institute produces the greenhouse gas protocols, and they define greenhouse gases under 3 different scopes or areas. Direct emissions, which is furnaces in the building, the wood-burning stoves. It also is gas combustion by equipment that is owned by the entity. So the Aldo Leopold Foundation owns a tractor and a truck and a car. All of that gas is part of their combustion. So you can start to see that this is already going beyond what we as architects and engineers do, but it is part of what a carbon analysis is, because the boundary is drawn around the organization, and it's everything the organization does, whatever you draw that boundary around. We drew the boundary around the building and the site and forest that we harvested the trees from, which gave us sequestration, which I'll touch on in a bit more detail. Scope 1 direct emissions were basically the wood, about 9 metric tons of CO2 emission from 2 3/4 of a cord of wood, 9 metric tons, which would be 2,200 pounds, or 2.2 English, or 1.1 English tons. They used measured around 2,100 gallons of gasoline per year. That's about almost 19 metric tons for 27, almost 28 metric tons of emissions in direct combustion. Electricity, a grid purchase of 48,000 kilowatt hours. The site generation was 52,000 kilowatt hours. There's actually around 24,000 or so that was sold out to the grid. So this is the total of what came in on the grid and the total of what was generated. The portion that was sold to the grid would be part of the overall net balance on the building energy demand. So that the net coming in on electricity was balanced against what was sold going out. I can see you're cogitating on a question here on that.
Yeah, I imagine have a pretty cloudy climate there, right?
Cloudier than here.
Yeah, so you get less out of those PV panels than, say,
We get around 1,300 kilowatt hours per year per peak kilowatt installed. That's the number that I use because it allows me to work with the standard sizing systems and quickly get to an annual production between 12 and 1,300 depending upon the final orientation. Although we had, there was 12 foot of snow in Baraboo, Wisconsin, broke all previous records, and we didn't get any production from the solar panels in December and January and half of February. We now have, there's someone who's hired with a snow rake to go out and clean them off. There's not a lot of energy coming in the winter. Our summers actually are not too bad. Our cloudiest periods are November and December. We don't really have, we get a lot of partly cloudy, which is still very bright in terms of sky brightness in the summer. So, but my rule of thumb is between 12 and 1,300 kilowatt hours per year per installed rated peak kilowatt. And I think that's the easiest way to work with PVs. We also had a green power contract purchase to cover our grid electricity coming in. We bought the rights to the carbon savings of some wind farm in Wyoming. This is part of the accounting that's going on in carbon credits. It is the game that I played in writing this up to meet the requirements for carbon accounting. I'm not convinced it's a good game, but it appears to be where we're headed. Personally, I prefer carbon taxes. I think it's direct, I think it's clean, and I think that if we're not careful with the cap and trade and credits, we're going to run into the same kinds of carbon accountants as we're ready to kick in the ass in AIG right now. But at the same time, that was the rules that I was going with, and there are things, that kind of purchasing of a credit, I'm not sure about. On the other hand, when we get down to forest sequestration, I think that has real reality in this project. But these are parts that aren't at all in the building, but the client actually considered them. The client said, we walked to our foundation office here in Baraboo. We're now going to drive 10 miles out into the woods to our new office in the woods that's down by the shack where Aldo Leopold wrote the book. And in the woods and in the prairie restoration that people who are coming to the classes are now going to be able to see. So he said we have to include employee commuting in the balance. And we went ahead and included business travel. I mean, I'm spending carbon to come out here to the West Coast right now. That's a part of the overall accounting on emissions. And solid waste removal. That bottom one is still a guess, but the top two are now closer to being measured values. And then managed forest area on sequestration. We haven't got this managed, but we're actually measuring it. We're going to be measuring growth rates, and we'll have growth rates for the 5 years post-harvest. The harvest was done back in 2004, 2005, that winter. And we'll get the growth rates about 5 to 10 years previous to that by going in and doing some boring. We've done a lot of work with the local forest service to actually go in and do timber cruises to determine what the carbon stand is in the building. We've documented every tree that was harvested that went into the building so that we know very much what the carbon removal from the forest is. And one of the things that we're trying to do is actually a very careful carbon balance that would allow us to look at the whole notion of using local wood in a building and how that both sequesters carbon and, if it's done properly, leads to better forestry management and healthy forests. And so in doing this guess, I used the rule of thumb that, that I have used from the Wood Burner's Encyclopedia, that a well-managed forest should provide about a quarter wood per acre per year. And when you translate that into what the environmental scientists give for carbon productivity and net carbon in the woods, that's a little bit smaller than what they say. It's about half that size. So this is actually a low estimate. My guess is that there's more sequestered than that if you do a well-managed forest. And so the balance ends up on carbon neutrality by all of this accounting, including the buying of the carbon credits, to suggest that we made it on carbon neutrality, even though we didn't quite make it on net zero. But again, this is a little bit, this has more of the balancing. The photograph on the left is pre-harvest. The photograph on the right is post-harvest. I've seen at least 5 trees that are missing on the photograph on the right. That was the way the harvest was done. The trees that were taken were the trees from the understory. The best trees were left there. The idea is that this will at some point become one of those great little patches of eastern white pine forest with trees with 4-foot diameter at the bases, with a standing carbon content that is about 4 times what it is right now. That is, it will actually have a good amount of sequestered carbon. There'll probably be 2 more harvests along the way to get there, maybe 3. And there is a variation in the amount of energy that is added to that wood as it goes into product. Peeling logs and using them as rafters gets the most structural strength out of them at the least energy impact, and you get all the volunteers out there and it becomes a community event. Site-based sawing of the timbers adds a bit more energy to the tree per board foot. It's done on site, air dried on site for a season before they're put into the building. It still is a lot less than shipping them in from somewhere farther away. The trees didn't move more than 6 miles from forest to building. Some of the wood goes off to a kiln that was about 75 miles away, comes back to local cabinet makers who hand make cherry chairs for the conference room. The building cost over $300 a square foot gross. About $120 per square foot of that, at least, if not $150. We haven't got all of the final details worked out. Went to 6 different contracts for carpenters and cabinet makers. A huge portion of the money that went into the building went into the local community and went into the labor to make this building from the local materials. There's a large amount that went to some very sophisticated mechanical systems and to the PV systems, but still a huge portion went to the local community. Probably 40% of every person who worked on building the building came to the open house for the building, in terms of the ownership that the people that made the building felt for that building. And you know, you would go in and it is, you know, all of the wood that they worked on. The controls installer that did all the wiring of the controls, he came in with his parents, his wife, and his 2 girls, and the oldest one, who was about 10, said, "Well, what did you do here, Daddy?" And he pointed to a Honeywell thermostat on the wall, and he said, "I put all of these in." I mean, you know, it's not anything necessarily special. He puts those in all the buildings, but it was a part of this particular building. And so it was a real ownership by the community of the project. And this is the meeting room that had, that still is before that wood burning stove was replaced. These chairs in the foreground actually were purchased, but they were chairs that were basically all recycled materials or sustainable yield harvest wood. All of the oak tables, the cherry floor, the pine trusses, the red maple on the ceiling, the cherry chairs, that's all built from the wood that was on site. And actually the carbon footprint for that kind of construction is a lot lower. And the use of local timber holdings for local materials, I think, really promotes the local economy in the same way we talk about farmers markets and connecting the farmer to the city in terms of growing. And so I'd like to end. This is actually a restored prairie on the site with the pines that Leopold had planted in the background. Even a prairie, over the first 10 years as it is going into place, will basically sequester carbon for 10 years at a rate faster than a forest as it's developing its root structures. Once a deep prairie is fully developed with the root structures that are going down 15 to 20 feet, it will no longer sequester more carbon. But a prairie also has a reasonable amount of sequestered carbon in it. And it is a great resource for growing ruminants. We have restored prairies in southwest Wisconsin that are being used by dairy farmers that are making artisanal cheeses that say that the milk that they get from the restored prairies is fine. Maybe not quite as good as from that pure clover, but basically there are a lot of ways to think about what it is that we're doing in the design of our building that really does move into the larger notion of what we're doing as communities and how we live on this earth. So with that, I'd like to close and leave you with some time for some questions.
I'm sure there are questions. If not, I've got lots.
You weren't getting any over the
No, over the internet today.
internet.
Okay, I'll reach this as far as I can. It'll be good enough.
Is this a mic?
It is.
That's it.
For John Glenn Hall. Just a few questions about the envelope.
Okay.
The floors, the slabs, how are they insulated?
The exterior wall is insulated with 2 inches of rigid. There's 4 inches of rigid underneath the floor slabs.
Continuous.
Continuous.
Great. And
I would not recommend a radiant slab system without continuously, at least if it's on the ground, you're going to lose more energy to the ground, as Frank Lloyd Wright did in some of his early houses,
yes,
if you don't do that.
And then on the wood floors where you put the fins underneath, what was your strategy there?
The wood floors, actually, the fins are a standard fin tube convector along the wall.
Oh, I see.
But we brought the air in for ventilation right underneath the fin tubes, so that the air in the winter came in through an air-to-air heat exchanger at lower than the room temperature, but went past the fin tubes into the space.
Oh, that's interesting.
The floor slab was fully insulated, 12 inches deep for the structure, and then additional rigid insulation under the structure, and then that was over a crawl space.
Ah, very interesting. And
Okay.
and your glazing.
We used a pellet glazing with a argon filling with a low E coating. The NFRC rating was on the fixed units 0.31 BTUs per hour per square foot per degree Fahrenheit, and 0.35 BTUs per hour per square foot per degree Fahrenheit on the operable units. But we modeled infiltration separately in the program, so we used the fixed model for the U value for all the glazing.
Okay.
Some of those numbers I still have in my head, some of them I don't.
Well, thank you.
Can't ask them about the roof.
All right, we might as well go to your treatment of the ceilings and roof. Overhead.
Well, let me see if I can. Whoop. The structure, as you can see, is an internal structural system. And the exterior walls, where we had a lot of windows cut in, we did 2x8 with 2 inches of rigid over the fully insulated 2x8 wall. Where we were on the north wall and the east and the west walls, the north wall we were cutting out the same cuts for the office windows all the way down. We used SIP panels. And we also used SIP panels over those roof rafters on the roof. Mm-hmm. And there are false rafter tails that come out around the edges so that you have your very thin roof edge, and the false rafter tail basically goes into a structural fascia board that is at the end of a SIP panel. So we've got a 12-inch SIP panel as a roof structure that is sitting over the structural frame. And by putting the structural frame inside the building shell, we're able to both show it off for what it represents in terms of the wood that was grown on site, and also do a better job of keeping a continuous insulated shell over the structure.
And one last question. How do you prevent moist air from getting up to your structural panels? In other words, do you have a vapor barrier above the interior surface that we're seeing here?
I can't answer the vapor barrier question on the SIP panel on the roof for sure. We do have a vapor barrier on the inside surface of the wall, so I would assume that we're doing that on the roof. But you know, without looking at that detail, my guess is that we do. We don't really have a moisture problem in the building. Quite the opposite. Some of the folks from the Forest Products Laboratory in Madison say we need to increase our relative humidity in the building for those wood floors that we have that are going to dry out too much. So the moisture in the winter is not as much of a problem. We were actually, in terms of moisture, more concerned about the summer. And in fact, the client in the summer had started out by just leaving the clear story windows open because they're worked with a crank handle that you've got to try to get on the, it's not a good detail. I still keep complaining to the architect, we've got to get a better detail for that. So he left them open, and then it got into August, and we had a very humid week in August, and the person who cleans did a mopping of the floor, and the water just didn't evaporate because it was humid and it was left open, and we were cooling the slab. And now they actually don't open the clear story windows. All the ventilation is just cross flow ventilation at the main level, and we have a control system where when the building operator turns the building into natural ventilation mode, all of the radiant floor slabs and air handling units are all powered down, And when it's in natural ventilation mode, if the dew point temperature inside the building approaches within 2 degrees any one of the slab temperatures, the lowest slab temperature that we measure, then there's a warning that an alarm that says that it is not appropriate for natural ventilation. So we do a kind of an interface where the system is able to tell the occupant what the dew point temperature is relative to what the floor temperature is. But moisture was more of a, we were more concerned about moisture on the slab when we were cooling with the slab than we were about the passage through the enclosure. We're using rain screen techniques on the outside with an air wrap and a vapor barrier on the walls. So I'm pretty sure they weren't assuming the SIP panel was the vapor barrier, but that they're running a vapor barrier above the ceiling. But
sounds like great care has been paid, and that's an amazing story about the humidity. Thank you.
Yeah. Well, it's a little more humid there than it is here. You don't have to worry about it quite as much as we do.
I just wanted to know, what was your time schedule as far as the construction and the design process? Like, how much time for design and then construction?
Design was initiated in the summer of 2004, but it didn't move very quickly because there was a lot of sort of fundraising that was going on during that process. And we provided some initial schematic design concepts to help out with that. The real meeting that really initiated the design process, design development and simulation and everything else, was in around December of 2004. Construction was completed around Earth Day of 2007. So so that's a little bit less than 2 years overall, from the initiation of design all the way to the completion of construction. Does that help?
Does the Forest Products Research Lab in Madison recommend air-dried members for the structure in lieu of kiln-dried?
They did not have any problem with air drying the structural members. You do need to let it go through a full season for air drying, and actually we had a structural grader come out, and based upon where the drying cracks were occurring, both the slope and the distance between the cracks, we got a final strength assessment for all of those members. So all of that was included in that whole issue. And in fact, structural grading is probably the biggest issue when you're talking about harvesting. But I pulled a couple of samples out, cut them out 2 inches square and whatever the proper height is, and went over to our engineering department and did some testing on them. And both of the pieces of white pine tested on ultimate strength and compression, pretty much right where you would expect it from published text. So that was just an added piece on top of that in terms of structural testing. I will say the structure for this building was redesigned 3 times. And it was because we were in a learning process overall with exactly what we could get out of it. We thought we were going to cut 2x members out of all of the timber. Then we thought we were going to cut, ridge rafters and so on. And we figured out we didn't really have enough to do that. And finally, I mean, we ended up with round logs because that was the most efficient way to work with what we had to build with. I mean, it's very different when you go in and design and say, well, we'll just order all of this from the local lumber supply and they'll have it shipped in by train from British Columbia or Northern Idaho or wherever it's being shipped in from. And being told, here's your pile of wood, this is what we want you to build the building out of. And the pile of wood was the 16-foot stems that were cut. I mean, we got one of those really nice harvesting machines that goes in, that you can literally destroy a forest in a matter of days, clear cutting it, but is also an intriguing enough machine that you can go in and cut the piece off of the stem and carefully pick the log up and out with the minimum amount of damage to other pieces. We did it all when the ground was frozen so that we would do the least amount of damage to the soil. So we had a very good bit of information, but it took the structural engineer and the architect 3 tries to figure out what they could do structurally with that pile of wood in the end. I believe it was someone from either Montana or Idaho that does round log trusses, and the seed hall and the workshop use round log trusses where there's steel rods for the tension diagonals, and the vertical are it's basically a triangular truss. The verticals are all compression, and then the top and bottom chords are round logs.
When I've done log structures, my engineer always says you've got to use Doug fir for the structural members, and you're using the pine, I think you said, on site. Did you have it tested?
We had it, well, I did some testing of the pine, although that didn't come into that part of it. The white pine basically tested out to be similar in terms of ultimate strength that you would have read in any of the testing literature. I mean, I carried it up to failure in both cases, but no, we used white pine, which was basically the standard building material from the late 19th century. The white pine in Wisconsin is what drove the lumber commodity market in Chicago until they ran out of that and had to move further west. Now, I don't know how long a span you're typically working with. Our spans here are running up to about I think 36 feet is the longest span, and they're spaced at no more than 12-foot centers. But actually, that part of the engineering was done by the group from either Montana or Idaho that basically did and certified the structural performance of those members, and they had to know what species it was because that's what we told them that they had. But that was actually done, that engineering was done outside of state by someone who'd worked with round logs. Now, why does your structural engineer suggest that you use Doug fir out of curiosity?
Well, and that was Doug fir logs.
Right.
And I understood that for the unmilled wood, that the pine was inadequate for his bearing.
Well, unless there's something unusual about how one wood material would, I mean, the only thing I could think of that would be a difference is if Doug fir doesn't creep and pine does, in the sense that concrete creeps. Because if it's just a matter of strength, you can size different materials for the stresses they're going to overcome. That's why I was curious as to why. I mean, I think Doug fir is a great structural material. It is really one of the better structural materials out there. But you know, white pine. I mean, it was the pine logs coming out, the white pine logs coming out of New Hampshire that the British used for their navy for so many years as a ship's mast, and we pulled.
They didn't have to meet codes.
No, they didn't. But I guess I'm saying, you know, the masts worked pretty well, and but you're right. Codes, and actually structural codes have become even more, not just for wood, but for everything, a bit more restrictive over the last few years than they have been in the past. But you know, I don't think, you know, I can't conceive of why the species would make a difference, I guess is what I'm saying. And no one from the Forest Products Lab told us that we shouldn't be doing it with the pine logs. There's a pretty good knowledge base there. Yeah.
I have a question about the water-to-water heat pump system.
Yeah.
From that schematic diagram you had put up there, it looked as if it was a closed-loop system.
Yes.
And then you said 16 vertical wells.
There are 16 vertical wells in 4 groups of 4. So we've got a line that will go out with four wells in parallel coming back. We've got 4 lines going out to 4 wells.
I guess my question is, Was the choice to drill vertical wells for the impact on the site, or was it for a reason of efficiency as opposed to doing a trench system with, you know, the loops kind of laid horizontal? I'm just curious as to why you went with that design decision.
I actually have not worked towards trench systems at all. We've always, if we can do it, gone vertically. The first project we worked on, Schlitz Autobahn, we did 90 wells that went down 90 feet. And one of the issues is that if you're doing a trench system and you're trying to take heat out of it in the winter and you're in a climate where the frost goes down 5 feet, you're going to probably need more linear feet of trench than you would of well. And so, you know, without, I mean, I typically have simply looked at a well as being more efficient than a trench. And there is the issue with a trench system then at taking up a larger area in terms of square feet to fully work with a trench. On this site, that would have been more area disturbed in terms of the overall lead impact. But this is actually all sand. I mean, it was a big sandbox. The guy that went around with the dozer must have felt like he was in a sandbox as a kid again. It was basically sand for as far as we went down, which is 320 feet. And it is out of the floodplain, but still only about 300 yards from the Wisconsin River. And so we figure that there is water in the wells, and we figure that that's water that's moving in the underground aquifer, so that we're really working with something much closer to a constant temperature throughout the year. The other thing we did with the wells was we did what was called reverse return, so that the hydraulic length or the friction head for every well is the same. The one closest to the building and the one farthest to the building all have the same amount of feet that they have to go through to go down the well, up and back, by taking a return out and then looping it back in so that the overall length is the same. That means that we didn't have to use balancing valves to try to be sure that each well would get the same flow rate. It's self-balancing. So that was another thing that we did on the wells. Yes?
Did you do any measurement of the capacity of the well to move heat in or out?
Yes, we did the standard capacitance test for a ground well. You basically drill a pilot well, and you basically, it's really a conductivity capacity test for the earth. And there's a standard set of procedures for doing that, and we include that in all the specs for what we do, because you cannot be sure of what you're going to get. I mean, we've worked in pure clay and pure sand, which is about the two extremes. Rock is likely to actually be maybe closer to clay, but pure clay really doesn't allow the water to go through. And there we ran the simulation for 10 years to see whether or not our net heating demand was going to cool the earth down over the 10-year period. And we spaced our wells 20 foot on centers instead of 15 because it was in clay. So all of those kinds of issues for ground wells, yeah, those are all procedures that we went through.
Well, we are about there. I want to thank you, Mike, for coming out. This was wonderful, an excellent presentation and a wonderful project. Since I'm going to take my chance to ask one question, since you've obviously worked through a lot of challenging issues on the project, and you've put this forward as one of the examples for carbon neutral and very close to net zero buildings have, and everyone's got their opinion. I want to ask, are there other buildings that people have pointed you toward that you think are comparable and or come close to competing or being a part of that same discussion?
Well, I'll take the last part, being the part of the same discussion, because I think it's less important. I mean, when Rick Federici, who is the president of the U.S. Green Building Council, and someone who basically says reading Sand County Almanac changed his life, he jumped on this building when he saw it. He came out to present the platinum plaque to the Aldo Leopold Foundation. And then he went around and said, this is the greenest building in the world. And what we've said to anyone who said that is, no, the shack that he wrote it in has no electricity, no running water, and Leopold and his family lived in that shack. That's the greenest building. It's much greener than this building. And I think that kind of sort of counting and competition isn't the issue, but the discussion is. I mean, I learned a lot from going into and visiting the Woods Hole Research Institute. And, you know, I can give you the names of architects that I think are doing interesting projects, and it's worth looking at what they're doing. I think Methune in Seattle is doing some very interesting work. There's some projects that EHDD in San Francisco is doing that are really quite interesting. Siegel Strain in Berkeley has got some interesting projects that are going on. Kieran Timberlake in Pennsylvania is doing some interesting work. The representative that they sent out to Milwaukee to this carbon neutral design conference that we ran, the representative from Kieran Timberlake's architectural firm was a graduate of Yale's Forestry and Sustainability program. And I knew he was a ringer with all the questions he was asking of the Aldo Leopold Foundation people about their forestry management, but he's working on resource issues and materials issues in Kieran Timberlake as a part of the way that they're approaching these things. And certainly McDonough and Associates is a firm. I mean, these are architects whose projects I go and look at to try to keep abreast of what I think is important that's going on out there. So I think there's a lot. I mean, for example, EHDD took a branch bank building in San Jose, California that you might find on any corner in a suburb or a city, and Ideas and Integrated Design Associates, an electrical engineering consulting firm who did a lot of work with EHDD, was doing this project, and Scott Shell at EHDD said, well, you should really do this as net zero. So they've done a reconstruction and rebuilding of an existing branch building into a kind of a nice net zero office building. Now, in the first year, it didn't make net zero, but they're doing the same thing we're doing. You know, going through and see what was going on. Their problem was the PV system just didn't work at all like it was supposed to. They were doing this PV integrated to the roof bit. But in any case, they still were working at it that way, and they're working at it with a rather mundane building that they've turned into something really very nice. And so I think that there's a number of buildings that are worthy of discussion, and it's enough so that there ought to be buildings sort of going on locally in the regions that you can really begin to talk about. We had an incredibly interesting breakfast discussion at the B&B that outside guests get to stay in down the road, which is really quite nice. And another one of the guests there works for the U.S. Department of Labor Statistics, and her office is in the new federal building in San Francisco, designed by Thomas Mann, this tall building that is supposed to be, you know, naturally ventilated. And her floor, which is the Bureau of Labor Statistics, complained the most, and they now have control of the windows, and they now feel that it's a little bit more comfortable than it was before. And actually, what's interesting in the discussion is getting into what people are saying about the buildings, as well as how they work and what we discuss about them as professionals. So that's, I guess, what I would suggest. And in terms of consulting firms, I've always looked at what Overp is working on. Borough Leopold works on some pretty interesting things out of New York City. But basically, there's probably a lot more talent locally than most people would think of or give credit for. And one of the things that happened in Milwaukee was on the first lead project we worked on, the Schlitz Audubon Nature Center, an architect from another firm gave his complete lead submission, lent it to the architect of the Schlitz Audubon Nature Center so that he could see what was required. And so when we finished that building, we lent our, that was sort of going from a lead silver, this one was a lead gold. We lent that, our full lead documentation to another firm that was doing their first LEED project. And usually we see ourselves in competition, but I think we're also in community. And so I would really encourage that kind of community learning that can really go on within the profession and locally as well.
Yeah, thank you. Well, we really appreciate your willingness to share the successes and some of the challenges, because those are where we obviously learn the most, and it's a good discussion, and we'll keep having it.
Well, thank you for having me.
Yes, thank you. Orders of business, if you didn't sign in, please do. And the next presentation is Thursday night, April 9th, same time, 4:30, same place. Thank you to Idaho Power, Better Bricks, to Northwestern Energy, and to Mike Utzinger for coming out.